Hello students, this is Anand Reshimkar from Department of Mathematics, Dayan College, Solapur. So we are going to start the syllabus from where we stopped. So just before we have seen the theorem which connects with which gives the relation between the normal extension and the splitting field. So after that we have to see this theorem which says let K be a normal extension of a field F which is of characteristic 0 and T be a subfield of K containing F, then T is a normal extension of F if and only if sigma of T is contained in T for all sigma belonging to GKF. So let us start with the proof. First of all, I will tell you the strategy that we are going to use here. In the first part, we are going to assume that sigma of T is contained in T for all sigma belonging to GKF, and we prove that T is a normal extension of a field F. T is a normal extension of a field F. To do this, we use the previous theorem, means to show that T is normal extension of a field F. The strategy is to show that T is a splitting field of some polynomial P of X over the field F. So once we have it, we can use the last theorem, which says that if T is a splitting field of some polynomial P of X over F, then it has to be normal extension. So let us start with the proof. So what we are given is K is normal extension of F and characteristic of F is 0. We know that every normal extension is finite extension, and therefore K is a finite extension of F. Further, we are given that T is a subfield of K containing F, something like this. So as K is a finite extension of F and T is a subfield of K containing F, T has to be finite extension. So this implies T is also a finite extension of F. But we know that the characteristic of the field F is 0 and T is a finite extension of the field F, then T has to be simple extension. T must be a simple extension. Now, if T is a simple extension of F, by definition, there exists A belonging to T such that T is equal to F of A, because by the name simple extension we mean that it is a field extension obtained by adjoining single element, so we can call that element as A. So far we have this T is equal to F of A. Now assume that sigma of T is contained in T for all sigma belonging to GKF, where GKF is the group of all automorphisms defined on K which are living elements of F fixed. So this is my assumption. Now I have to prove that T is a normal extension of f. T is a normal extension of f. As k is a finite extension of f, we must have degree of k over f equal to n when you have any some finite number. Also, by the theorem or by the corollary, since k is normal extension of f, we must have degree of k over f is equal to order of gkf. But we have assumed that degree of k over f is n. It means order of gkf must be n, means gkf must contain n distinct automorphisms. So let those automorphisms be sigma 1, sigma 2, sigma n be n distinct automorphisms in GKF, and as it is a group, one of them has to be an identity element. So sigma 1 is identity element of GKF. Sigma 1 is identity element of GKF. Further, as A belonging to T, which is equal to f of A, and sigma of T is subset of T for all sigma belonging to GKF, we have sigma 1 of A, sigma 2 of A, sigma n of A belonging to T. So by the assumption sigma of T subset of T, it means when we apply any sigma from GKF on any element of T, the resulting element should be again in T. So by that you can write sigma 1 of A, comma sigma 2 of A, and so on sigma n of A as members of T. Now consider a polynomial. Consider a polynomial P of x, which is equal to x minus sigma 1 of A, and so on x minus sigma n of A. So we have considered a polynomial P of x is equal to x minus sigma 1 of A, x minus sigma 2 of A, and so on x minus sigma n of A. As sigma 1 of A, sigma 2 of A, sigma n of A are members of T, I can say that this polynomial is a polynomial over T. On simplifying, I get a polynomial of degree n, x raised to n minus alpha 1 x raised to n minus 1 plus alpha 2 x raised to n minus 2 plus so on plus minus 1 raised to n alpha n. As I have named these coefficients alpha 1, alpha 2, alpha n, I have to specify what their values are. So their values are alpha 1 is equal to sum of the roots sigma 1 of A plus sigma 2 of A plus sigma n of A. Alpha 2 is equal to product of the roots taken 2 at a time means summation I less than j sigma I of a into sigma j of a, and so on. Alpha n is a product of roots, means it is sigma 1 of a into sigma 2 of a, and so on, sigma n of a. As we have seen earlier that these are elementary symmetric functions, and we have also proved in the previous two theorems that these elementary symmetric functions are invariant under a group GKF. By this it means all these elementary symmetry functions are invariant under all the elements of GKF, and that is to prove that sigma of alpha I is equal to alpha I for all I and for all sigma belonging to GKF. For this we have to first prove that sigma I and sigma j are distinct elements of GKF whenever I not equal to j, that is whenever sigma I not equal to sigma j. And why it is so? Because sigma I and sigma j are the members of a group. Sigma is again arbitrary member of a group, and in the group closure property holds, and therefore sigma into sigma I and sigma into sigma j are always members of GKF. So what we left to prove is sigma I and sigma j are distinct. Suppose they are not distinct, so means we are proving this by contradiction. So if so consider a polynomial p of x is equal to x minus sigma 1 of a, x minus sigma 2 of a into so on x minus sigma n of a over t. On simplifying we get x raised to n minus alpha 1 x raised to n minus 1 plus alpha 2 x raised to n minus 2 plus so on plus minus 1 raised to n alpha n. As I have named this alpha 1, alpha 2, alpha n as coefficients, I have to specify their values. So there alpha 1 is equal to sigma 1 of a plus sigma 2 of a plus sigma n of a. That is, again alpha 2 is product of the roots taken 2 at a time. So summation over I less than j sigma I of a into sigma j of a, and so on. Alpha n is equal to sigma 1 of a into sigma 2 of a, and so on, sigma n of a. Now we are going to show that this all alpha 1, alpha 2, alpha n are invariant under each element of GKF. That is to prove that sigma of alpha I is equal to alpha I for all I and for all sigma belonging to GKF. Before that, what we have to prove is sigma into sigma I and sigma into sigma j are distinct whenever I and j are distinct. And why we need to prove this is, as we are going to apply sigma on each alpha I. So on the right hand side I get sigma into sigma 1, sigma into sigma 2, sigma into sigma n. Right now, as we can see, there are n terms which we can visualize here. So on applying sigma on alpha 1, it should again produce the n distinct elements, so that I can write that is again equal to alpha 1. Similarly for alpha 2, similarly for alpha n. So for that, suppose I not equal to j, so that sigma I not equal to sigma j, and I have to prove that sigma I not equal to sigma j. That is, I not equal to j implies sigma I not equal to sigma j. But I will prove this by contradiction. Suppose on the contrary that sigma I is equal to sigma j, but these are the elements of the group, and in the group we know that the left and right cancellation laws holds. So by the left cancellation law I can cancel this sigma, so what I get is sigma I is equal to sigma j, but it is contradiction to our assumption that sigma I and sigma j are distinct. So the sigma into sigma I and sigma into sigma j have to be distinct whenever I not equal to j. So now consider sigma of alpha 1, that is equal to sigma of sigma 1 of A plus sigma 2 of A plus so on sigma n of A, which is equal to sigma sigma 1 of A plus sigma 2 of A plus so on sigma n of A. Now as sigma 1, sigma 2, sigma n all are distinct, means they are n in number. Further, sigma 1, sigma 2, sigma n are again members of GKF. Each sigma I has to be equal to some sigma j, and therefore what I get is it is equal to alpha 1. Similarly, I can show that sigma of alpha 2 is equal to alpha 2. So on, sigma of alpha n is equal to alpha n. And this proves that each alpha I is invariant under sigma. Each alpha I is invariant under sigma. But this sigma belonging to GKF was arbitrary. It means each alpha I is invariant under every sigma belonging to GKF. Every sigma belonging to GKF. But this means we have proved that sigma fixes all alpha I. Sigma fixes all alpha I for all I running from 1 to n. But sigma is a member of GKF, and we know that in GKF the elements of K which are being fixed by all the members of GKF are nothing but members of F. And here we have proved that each alpha I is being fixed by sigma, means each member of GKF. It means all these alpha I belonging to F for all I where I is running from 1 to n. This implies P of x is a polynomial over F. P of x is a polynomial over F because alpha I are the coefficients of P of x. Also we can see that P of x splits over T as x minus sigma 1 of A, x minus sigma 2 of A, and so on, x minus sigma n of A. Further, this sigma 1 is identity map, means sigma 1 of A is A. So P of x is equal to x minus A into x minus sigma 2 of A, x minus sigma n of A. Here we can see that x minus is a factor of P of x, and therefore A is a root of P of x, which is a polynomial over F. But A is a member of T. Further, we also know that T is the smallest field which contains f and a. In other words, A generates T. It means no field which is properly contained in T contains the root A, and therefore we can say that T is the smallest field containing all the roots of P of X, and this means T is a splitting field. T is a splitting field of f of x. But this proves that T is a normal extension of f. T is a normal extension of a f. So what we have proved is sigma of T is contained in T for all sigma belonging to GKF implies T is a normal extension T is a normal extension of f. So this is what we proved. Now let us see the converse. Okay, now in the converse we have to prove that T is normal extension of f implies sigma of T is contained in T for all sigma belonging to GKF. So assume that T is a normal extension of f. So again by corollary we see that T is a finite extension of f, and order of degree of T over f is equal to order of GTF. Now say degree of T over f is m, means order of GTF has to be m, means there must be m distinct automorphisms, say psi 1, psi 2, psi m be m distinct automorphisms in GTF. As they are in GTF means they are fixing all elements of f. As T is normal extension of f, the elements of f are the only elements which are being fixed by these automorphisms. No element which is outside f is fixed by psi 1, psi 2 and psi m. Now again consider polynomial p of x is equal to q of x. Instead of p of x we will take q of x as x minus psi 1 of a, x minus psi 2 of a, and so on, x minus psi m of a, where psi 1 is identity map. Here since T is normal extension of f, it has to be a finite extension, and therefore it has to be simple extension, and therefore T must be of the form T is equal to f of a for some a belonging to T. Now as we have already proved that this, as q of x is splitting over T, means psi 1 of a, psi 2 of a, psi m of a all are elements of T. Now on simplifying I get q of x is equal to x is to m minus beta 1 x is to m minus 1 plus beta 2 x raised to m minus 2 plus so on minus 1 raised to m minus 1 into beta m, where again these beta 1, beta 2, beta m are elementary symmetric functions. Elementary symmetric functions. Further, we can similarly prove that all these beta I are invariant under each psi belonging to GTF, because so this implies all these beta I belonging to F. So Q of X is a polynomial over F. Q of X is a polynomial over F. Also, psi 1 is identity. So psi 1 of A is A, implies A is root of Q of X in T, and T is contained in K, so A is root of Q of X, which is in K. Now to prove that sigma of T is contained in T, we have to show that sigma of T belongs to T for all T belonging to capital T.